Good morning, Jim Chastain with EasyPower. This is the part 2 refresher on arc flash results, focused on new tool users that are basically starting their first one line and trying to, as much as possible, help people get up and running without a lot of headache. And by all means, don't let yourself be stopped by initial frustrations. You have access to a fair amount of help, both in guidance for just starting using the tool and in more understanding of how the tool works in your particular system. So with that in mind, let me kind of launch into our presentation. We're going to assume that the data has already been collected, and frequently people will ask, do we really need all that data when we're doing a one-line diagram? The answer is yes. And the more you play with the tools before you start data collection, the more you will appreciate the need for the data and the other aspects of data collection besides just writing numbers down, just to observe, frankly, to gain a more intimate knowledge of your system and what constitutes a dangerous situation that you may or may not have been aware of. Basically, the one-line diagram builds the file that contains the data elements, and as you take your time and start with a very simple system and understand how these data all plays together, I think you will, and not be afraid of starting over if you're not getting quite the results you expect with your first drawing. I think you will be much more satisfied with the end result, again with a little bit of trial and error on the front end. In reality, poor construction and poor modeling can actually be a significant issue. I mean, it's one thing to be ignorant of the dangers in the system. It's another thing to make it only a halfway attempt, when in reality the people doing the data collection are very frequently the ones that would most benefit from having a safer system. So that's the function of the short circuit analysis, is to ensure that the existing and new equipment ratings are adequate to withstand the potential max worst case event that a short circuit would pose within the electrical system. Very frequently, because arc flash was not that well understood back in the turn of the century, if you will, pre-1998, a lot of buildings were designed inadvertently with arc flash hazards pretty much built into them, and it's not until we start to do arc flash studies that people realize how dangerous situations are and learn to either deal with them, mitigate the energy problems, or procedurally take care of situations that could potentially be harmful during normal operation. So the short circuit study determines the parameters needed to evaluate the protective devices and then helps identify problem areas in the system. So what the tools will provide for us is the ability to fault a bus or fault all the buses, and then as we do that, see what the individual bus currents and voltage results will be. Likewise, it deals with X over R ratio compensation because this is a key element in whether or not the protective devices will actually work to their guaranteed ratings. And we have the ability to look at different types of faults with the tools and what that effect is on our protective devices. So with this, we're going to jump into the short circuit focus and talk a little bit about the controls. Every time I do a demonstration, I reiterate the fact that as you install the tools on your system, there's an automatically built-in folder in the EasyPower 9.7 one-line subsystem or subfolder called samples. And these are pre-made one-line construction that are used in the tutorials that are included when the tools are installed. And I encourage you to not only go through the tutorials for your own edification, but make sure you play with the samples. In this case, we're going to be using Protection 1, which is used in several of the illustrations or the tutorials. All right, so the advantage here is we have a fairly well constructed one-line diagram that includes protective devices, relays, both up system and downstream panels and MC systems. And what we're looking for is what the short circuit focus can actually give us as far as results. So now that my one-line diagram is constructed, I'm going to change the focus of EasyPower tools to short circuit. And as I do that, if I don't have any mistakes, it will basically give me a clean screen and a new set of icons here to the left. If I do have a mistake, for instance, if I have, for some reason, a cable hanging out here that hasn't been characterized or terminated, and I try to change focus to short circuit, it will give me an error report that I can either look on the list or highlight it in red. And in this case, I know what I did wrong, so I'm just going to undo it, which is a Control-Z, and we're back to ground zero. I want to enter short circuit focus, and I'm going to look a little bit about some of these, what these icons really mean. So first of all, if I have no bus selected, all right, I'm just selected out here in the middle of the white area, I have the ability to look at half cycle current, 5 cycle current, and 30 cycle current on any type of fault. In this case, by default, we're selecting a balanced 3-phase fault. So this is what's called as a bolted fault. We can also look at a line to ground fault, a dual line to line, in which case it says we're really going to be looking at B and C phase because that's what's used in the simulator for faulting. And then we can look at a line-to-line fault. Same thing, a B and C phase there. For starters, we're going to be looking at balanced 3-phase, only on the A phase. And let's just look at the first half-cycle fault. Select this one bus and fault it. And what we see are, in this case, 14,587 amps that come down from the utility, 521 amps, 1,302, and 2,343 coming back from each of these loads. Okay, how do I know what these units are? That's part of my short circuit options setup. If I go to the short circuit options and look at one line output, it says the display units for fault current are symmetrical kiloamps. So I can look at kVA or kiloamps, MVA or per unit. So let's see what per unit is. And here we got 0.216, 0.541, 6.06. So for me, it's making more sense if I stay on kiloamps. Likewise, I can select symmetrical, asymmetrical, which is a big difference in the half-cycle display, or a combination of max symmetrical and max asymmetrical. All right, so we're showing max symmetrical and max asymmetrical. While we're there, so this is essentially a DC offset that's effective if we get a fault at a varying place in the cycle of the AC circuit. And so the worst case, there could be as much as a 5,000 amp pulse differential because of that DC effect. If we look at what's going on at the 5-cycle point, you can see it's much less, the offset, because by this time any DC effect will have essentially bled. If we look at 30-cycle, it's pretty much gone. All right, let's go back and look at our per unit. So I'm going to go back to my short circuit. Excuse me, fault current, symmetrical, kiloamps. And we're also looking at, now it says remote bus per unit, and for the remote bus coordinates or magnitude, we're looking at magnitude and then magnitude and angle, and we'll show that in just a second. As we apply this, what we've selected now is we're on a half-cycle fault, bolted 3-phase. I'm picked symmetrical kiloamps, and so the branch current is symmetrical kiloamps, but we're showing per unit voltage on the bus. This is a remote bus. So this bus over here is 73%. Normally it's at 480 volts, so this will be 73% of that value. And then this is the power angle, the power angle on this particular bus compared to the utility. So it's a minus 90 degrees, which is a pretty drastic shift. That confuses me. I'm going to go back to vector coordinates and just show the magnitude. All right, so what we've done now is we faulted this bus. We see the direct short circuit currents, but now we also see the contribution of branch currents from any remote bus and the effect on its voltage. Whereas on this particular bus, we're showing current on the oblique. On the remotes, we're showing voltage, and this is per unit. If I select in the white area and fault the buses, then we go back to just branch currents and bus totals. So this will be 14,000 amps down from utility, 521 amps, 1,000. All that's going to add up at a vector sum for the bus loading. And likewise on this panel, we'll see 8,742 coming down, nothing coming back from the load because apparently we have nothing down here on the load. Okay, so that's current, half cycle fault current. A couple other things I want to point out while we're here. In fact, I'm showing B phase, and since it's balanced, it doesn't matter. We can show all three phases by selecting these three icons, and again, it's balanced, so all three are the same. If we go to a line to ground fault, we see that we have basically a balance in the two that aren't grounded and a higher current that's essentially offset at any given point by the ground current. If we go a line to line, you'll see that we have a balanced fault between the B and C phase and only bleeder current from A. And if we have a line to line, we see the same results without the ground contribution. Okay, again, there's a lot more to the short circuit module besides just arc flash calculations. Likewise, if you want to get into positive sequence, negative sequence, and zero sequence, this will all be affected by the type of fault. Again, a balanced fault, everything will be positive sequence. If we have a line to line, we'll see, it's when we have a line to ground that we'll see the negative sequence and zero sequence. And we have a line to line, we'll see offsetting currents in the B and C phase. All right, back to a balanced load, A phase, half cycle. We can choose to use, if we look in our short circuit options, again, the hazard controls for arc flash. This is what controls the calculations of incident energy in the EasyPower tool suite. We're starting off with IEEE 1584. In this case, we're excluding main for some reason. The tool automatically compares 100% and 85% of the arcing current value to calculate the worst case time or incident energy. The current that it uses for calculation is selected by this control. Right now we're set up for momentary current. If for any reason we wanted to select interrupting or 30 cycle, we would do it here. And so as we produce incident energy, let's just stay with one bus and fault it. What we're showing here is the incident energy calculated on this bus using the 30 cycle current. So it says, and we're excluding main, which means we're not including the protective device of anything immediately upstream. If we use interrupting current, we'd expect that value to go up because interrupting at the 5 cycle is a higher value usually. And if we were to use momentary, which is usually requested or implied, we get the highest value. Now, if we go back and look at our short circuit, our arc flash spreadsheet, we'll see that this particular bus is protected by R7, which is this relay up here, and that's basically disregarding the effects of this relay because we told it to exclude the main. The air gap, the bolted fault current, and the arc trip time, this is the trip time of this particular relay. The reason for kind of pointing that out is when we get back to our controls, we want to make sure that we're adjusting the right one. So if we were currently adjusting the trip time in R8, thinking that it was controlling this incident energy, we'd be missing the boat because right now the calculations are being controlled by R7. All right, that's a function of exactly the setup in this particular control area. So as we apply now the main breaker to include the main, we come back and see now the refiner bus is being protected by R8 because we're including the main, and now our trip time is down to 460 milliseconds, and that's considerably longer than a half cycle. And the reason for kind of pointing that out is if we were looking at the interrupt rating or interrupt current, it would be lower because some period of this arc is going to happen beyond the half cycle. I guess what I'm trying to get at is the most accurate calculation is actually the integrated mode, which allows us to take that part of the current, of the fault current, which occurs in half a cycle, plus that part of the fault current, which occurs in the first 5 cycle, plus the lesser that occurs out beyond that in the balance of the 30 cycles, and adds it up. And so consequently, you end up a little bit more accurate calculation of what the fault current total in the incident energy would actually be. So that's one way to kind of deal with incident energy calculations. Okay. Probably rambled more about that than I meant to, but hopefully I didn't confuse anybody. All right, other reports, icons, modify the analysis. Okay, so that was essentially everything that's in short circuit controls, arc flash hazard. This box controls calculations. This particular check mark, if for some reason you're not producing the arc flash hazard report, it's what produces that. And it's a very, I think, probably the second most important document aside from an updated one-line diagram that we need to be generating. And then as far as actual reports in a spreadsheet format, we create both high voltage momentary for momentary, 5 cycle, 30 cycle, medium format, and equipment duty. The equipment duty ends up being a lot more important, I think, than most of us first realized, or that I first realized. And as you see what it produces or what value it is, I think you'll become more enamored with it. So by picking up those check boxes, we're going to fault the bus one more time, and we'll see that all those reports now are in our Windows list. So the high voltage momentary report looks like this. This tells us the bus name, the voltage, the symmetrical current, X over R ratio, the asymmetrical current, and then the test environment that the manufacturer used for each of the devices, for each of the types of current. And whether or not our guard band is, our safety guard band is adequate to meet the worst case scenario, right? Then there's the high voltage interrupting report, same thing on the higher voltage side. There is a 30 cycle report. And again, this is just for the one bus because that's all I have selected. If we don't select, I want to see the equipment duty too. Of course, it doesn't show me anything because there's nothing, a violation there. The same thing is available if I just click off any bus and fault all the buses. Now all the reports will be generated for all the buses, and I've selected one that showed me only the violation. So let's come back here, include all devices in my equipment duty report, and now we have all the devices for each of the buses. So main switchgear, manufacturer, the style, the test standard that the factory guarantees, or the test that the factory guarantees, the rating that we're going to be exposed to, and then how much headroom we have based upon compensated calculation against the X over R environment that the test was made at. Okay, when you see anything highlighted in red, that means you're within 10% of the safety factor, or you've exceeded it, and in which case you want to pay attention to it, because that means that piece of equipment may not operate as spec'd. Okay, that pretty much covers short circuit. Our arc flash spreadsheets produced or shown in conjunction with the one-line diagram with this icon here. We showed briefly what find and select is last week. We'll talk more about Scenario Manager later. And I think that does it for today. Appreciate you joining in. Any questions, please contact us at techsupport@easypower.com or shoot me an email, jim@easypower.com, and we'll help you out. Talk to you next week. Have a good one.